going to talk about completeness of interpolation procedures. And this is a work with Stefan Hetzel, and this is published at Logic in Computer Science this year. Okay, so I'm talking about interpolation algorithms. Let's recall what they are. So it's a property of a logic. So we say a logic L has an interpolation property, if for any implication which is true in the logic, for each A implies B, there exists a formula in the middle. What do I mean by in the middle? It means that A implies C is in the logic and C implies B is in the logic. And C only uses the variables which are common between A and B. Okay? So this is the interpolation algorithm. And I was in Vienna visiting Matthias Bas. And Stefan came to me and asked me about the problem, about interpolation, about this problem, that whether I know if every interpolation can be obtained from an interpolation procedure. And I said I don't know, and it was surprising to me that nobody else has done this, so this initiated our study together. So we want to gauge the expressive power of interpolation algorithms by answering to this question that which interpolants we can obtain from an interpolation procedure. And we initiate the study of completeness properties of interpolation algorithms. What do I mean by completeness properties? It's in the next slide. So the question basically is that you fix a calculus, G, and then you fix an interpolation algorithm for this calculus, let's say I. Right? So these interpolation algorithm I and calculus G are fixed. Then you ask whether for any valid implication A implies B, and for any interpolant C of this implication, so these are as input, can we find a proof pi in the calculus such that I of pi will be C? So can we find a proof for A implies B such that the interpolation algorithm applied on this proof will output the interpolant C? So as you can see, the implication is given and the interpolant is also given, and we are asking about the existence of this proof. Yeah, so this is the completeness of interpolation algorithms. And
sorry, can you go back to the previous way? The nature of pi, yes.
Here?
The form. Yes. So why is pi here?
So this is a property about the logic.
Sure.
But we can prove this property about the logic within a calculus. So you fix the calculus, and there is an interpolation procedure inside the calculus. And I'm not talking about...
So it's related to the I operation that given a proof will extract the interpolant.
Yes.
Okay.
Yes.
So this is the... Okay.
And being an interpolant... Yes. Being an interpolant means satisfying these conditions.
And pi is what kind of a proof? What does it prove?
It proves this formula, A implies B. So it's a proof of A implies B. But then there are some procedures in the middle that in the end you will find the interpolant C.
Okay, good.
Yeah.
Isn't it that the normal Craig interpolation theorem says that not just the variables are among the common ones, but also relation symbols, function symbols, and so, or is that what you're meaning when you say variables?
That's very good, but now I'm only talking about propositional logic, so we don't have any relations, so it's not first order.
Okay.
To make it easier.
Oh, okay. Mm-hmm.
But you're right, for first order we also have those conditions.
And then yet another question, sorry to slow you down. Is it the case that there is a unique maximal or minimal C associated either with propositional logic or whether you can put conditions on L to say whether such a thing should exist?
Yeah, so these are related to uniform interpolation and not linear. But for instance, for Craig interpolant, we can have many interpolants.
Okay, thanks.
So, practically, why this study is relevant or important is that it gives us a guarantee that we can find a good interpolance, whatever good means in the area of application that you want. So this question, which was asked by a computer scientist to Stefan, was that, for instance, suppose that I have a good interpolant, maybe I have found it semantically, and can you find a proof such and such? So to find good interpolants, now the completeness result will give us an insurance of finding this good interpolants. And our results, what we have found in this area is many incompleteness and several types of completeness results. For standard interpolation algorithm, which is known in the literature, for two most important calculi, resolution and sequent calculi, for propositional model and first order logics. But here I have made sequent calculi and propositional logic both because I'm going to talk about this thing here. Okay, so I wanted to first fix the calculus and fix an interpolation procedure. So I'm now fixing the sequent calculus, LK, for propositional classical logic. Look at the language. I have negation, conjunction, disjunction, and implication. Gamma and delta everywhere here, they mean multisets of formulas, meaning that the order does not matter, but the repetition of formulas matter. And a sequent is an expression of this form, gamma double arrow delta, which means the interpretation of this sequent is the conjunction of formulas in gamma implies the disjunction of formulas in delta. And then LK, the sequent calculus LK, consists of these axioms and rules. So the axioms is the identity axiom and the bottom axiom, and then left and right rules for each connective. For instance, we have left and right conjunction rules for disjunction, for negation. We have structural rules, weakening and contraction, right and left. And one more thing, the sequent above the line is called premise, below the line conclusion. And of course, we have the cut rule. This formula A is called the cut formula. Okay, so I'm going to talk about fix this system, this calculus, and then also fix the interpolation procedure. But before that, let me give you some notation. So by LK at, I mean LK which only allows cuts on atomic formulas. So as I mentioned here, this A is the cut formula. If you only allow this to be atom, then it is atomic cut. So LK at is LK with atomic cuts, and LK minus, I mean cut-free LK. So LK without the cut rule. And then our results are, I'm going to talk about these two systems. One more notation is split sequent. It's basically partitioning the left-hand side and right-hand side of the double arrow by this semicolon. And this expression simply means that gamma 1, gamma 2, double arrow delta 1, delta 2 is a sequent. And now the interpolation procedure. So let's pi be a proof of this sequent in LK with atomic cuts. So you see the partition here, right? And then I want to define the Mahara interpolation algorithm, which is one of the most used, and this is the standard interpolation algorithm. I denote it by M. So this algorithm applied on a proof pi will output formula C, such that these two conditions hold, that gamma 1 double arrow delta 1 C is valid in LKS, and gamma 2 and C double arrow delta 2 is valid, and the variable condition. So the variables of C is in the intersection of the variables of gamma 1 delta 1 and gamma 2 delta 2. Okay? So what I'm doing is that to define the interpolant for a formula, I go to the sequent calculus. For every sequent, I define how I can use this algorithm, and I do it recursively. So if I have a proof of the sequent, and basically the formula that is given, then in the end, I will get the interpolant. And this notation, C, sometimes this C I write it about the double arrow. So I have to define the algorithm recursively. So first, if pi is an axiom, what we do, if it is an axiom, we look at the partitions of the atom. So either the axiom can be the identity axiom or the bottom axiom. So for instance, the first partition is that P is on the left-hand side of the semicolon in both sides. And then you can easily check that what this interpolant should be. So P double arrow P and C, and C double arrow nothing. So the only thing that fits here is the bottom. Right? So this is how for axiom I define the interpolant. Also similarly for other kinds of partitions and for bottom. And the variable condition is also easy to check. For instance, here, the interpolant must not have any variable. Why? Because it should be in the intersection of the left-hand side of the semicolon and the right-hand side. And you can see that the right-hand side is empty, so it should be empty. So this is how I define for axiom. Then for one premise rules, conjunction, so for instance, these are one premise rules, that they have only one premise in the above the line. So for all these rules, it's easy to see that the interpolant of the conclusion is the same as the interpolant of the premise. We don't change it. And for the two premise rules, that are only these rules, then you can easily check that the interpolant of the conclusion will be either the conjunction or the disjunction of the interpolants of the premises. For instance, for the left conjunction rule, based on this is the main formula, being on the left-hand side of the semicolon or on the right-hand side of the semicolon, you can define this interpolant to be conjunction or disjunction of the interpolants of the premises. And that's it. So this is the whole procedure. And then what is the theorem? The theorem is that let pi be a proof of A, semicolon, double arrow, semicolon, B in LKF. Then the interpolation algorithm that we just mentioned, applied on pi, outputs an interpolant for A implies B. So you wanted to find an interpolant for A implies B. What we do, you put A on the left-hand side of the semicolon, B on the right-hand side of the semicolon, and find a proof, and start from the leaves and compute the interpolants up to the conclusion. So this is the theorem, and is this clear? And let's see an example. So for instance, this formula P and Q implies P or Q. This is a proof for it. So starting from the leaf, the interpolant is P. It's a one premise rule. The interpolant doesn't change, and the interpolant doesn't change. So, and you can check that this P is an interpolant indeed, because P and Q implies P, and P implies P or Q. But this is not the only proof of this sequence, right? You can come up with different proofs, and based on different proofs, you can get different interpolants. So for instance, this proof, which is not as effective, but we have it. So it starts with P double arrow P. And so here we have P, here we have top one premise rule that doesn't change the interpolant, but now we use cut on P. And then based on the rules for cut that I didn't show them to you, we have the conjunction of the interpolants of the premises. One more definition, a formula is in negation normal form when negations only apply on atoms and the other connectives are conjunction and disjunction. And a very easy observation is that the interpolants that we construct from the Majara interpolation algorithm, they are all in negation normal form. So now we have our first incompleteness result. Before that, let me define syntactically complete. So I say an interpolation algorithm I is syntactically complete if for any valid formula A implies B and the interpolant C, I can find a proof pi such that C is exactly I of pi. So it means they are syntactically equivalent. And our easy observation is that the Majara interpolation algorithm is not syntactically complete. Because as I mentioned, that all of the interpolants are in negation normal form. this negation P is an interpolant of P implies P, but we cannot find a proof such that M of P will become exactly negation P. So it means that this definition is not nice, so I change it, the completeness notion, to semantically complete by saying that this C should be logically equivalent to I of pi, not syntactically equivalent. And from now on, by completeness, I mean this semantically completeness, and I don't use the semantically anymore. And now another incompleteness result, which is for LK without the cut rule. So consider this implication P and Q implies P or Q. It has 4 interpolants, P, Q, P and Q, P or Q. And it is easy to prove this proposition that the Malhara interpolation in LK without cut is not complete. And the counterexample is this formula that we like very much because it's a source of our incompleteness results. So I fix my Hara algorithm and I fix LK minus. Then I get the input P and Q implies P or Q, and the interpolant P and Q or the other one. Then it's easy to show that I cannot find any proof in LK without cut, such that the M of pi will be one of these. Okay. So this is one incompleteness result, and I think I have time to only show you one completeness result for LK with atomic cuts. So we saw that for LK without cut, we don't have completeness. But if we just add cuts for atomic formulas, then we get the full completeness. So the theorem says that Malhara interpolation in LK with atomic cuts is complete. And I'm going to show this, to give you a sketch of the proof only by an example. So I want to say that for any formula A implies B, and for any interpolant C, I can find a proof such that the interpolation outputs this C. Okay? Outputs a proof such that the interpolant is this C. First, what I do is that I change this C to a conjunctive normal form. So it's a conjunction of disjunction of formulas. So let's call them C1 up to Cn, right? And since this C is an interpolant, it means that A implies C is valid and the other one. Okay. So what do I get here? Since A implies C is valid, it means that A implies any of these Ci's is also valid. Okay, let's look at the example. So this is my A, P and Q, and this is my B, P or Q. And my C is P and Q. So it is in CNF. So first, if it's not, I write it in CNF in conjunctive normal form. And I look at each conjunct. Here I have 2 conjuncts, P and Q. And then what I do, I say that since A implies C is valid, it means that A implies each of these conjuncts is valid. I somehow, this part, I find a proof of A implies each conjunct such that the interpolant is that conjunct exactly. So for instance, for this conjunct, I provide a proof P and Q double arrow P. Let's call it pi 1. And the interpolant of this pi 1 is P. Similarly for Q.
5 minutes.
Okay. And then, so this is the first part that I use this part. What about the other part? I have to use this information somehow. So this part uses cuts on atoms. For the next part, I said that C is of this form, conjunction of disjunctions of formulas. This means that for any combination of choosing a literal I mean an atom or a negation of an atom. For any combination of choosing a literal from the first conjunct, from the second conjunct, up to from the last conjunct, I can prove that these formulas implies B is valid. And this is exactly what I'm doing here. So I have 2 conjuncts. The only combination that I have is choosing P and Q, double arrow B. And for this, since this is provable, I take a cut-free proof, and I prove that the interpolant can be shown that it is always top. And then I use cuts on atoms to find the proof for the for the sequence itself. But note that I had the interpolants for P and for Q, and I have a lot of tops. And based on the interpolation procedure, all the time, the cuts will produce conjuncts. So in the end, I will have the first conjunct of the interpolant C1 and C2 and Cn, and a lot of tops. So which is equivalent to C1 and C2, which is equivalent to C. So I know this was hand-wavy, but I hope it gives you a sketch of the proof and intuition of how it works. So this is the completeness results for Manhar algorithm for LK with atomic cuts that we proved, and it is complete. So summary of our results is that I showed you the propositional LK is complete and LK with atomic cuts, and the propositional LK without cut is not complete. So after this part, we were thinking of how we can expand, how we can get a completeness result for LK without cut. And this is basically the most difficult part of the paper, that it needs a lot of definitions, and it's very involved. We have for first order LK with atomic cut, which is even incomplete. And for another system resolution that I mentioned, it is incomplete. And for modal logics, which is very similar to the classical propositional logic, the cut-free versions are incomplete. And if you add cuts on atoms and box formulas, it is complete. So this is all the results that we have so far. And thank you.